This is summer 2011, Math 263, Test 3, number 1. Consider a solid E bounded by z equals r squared and z equals r. I think the first thing we want to do is to sketch what they look like. Okay, z equals r squared. If we think about that, in class, this is the way I teach you. First, suppose you have two-dimensional plane with rz, and the equation of this, if we try to graph it, is actually a parabola, like a regular x squared type, right? I use r positive only. That's what it looks like. Now then, if we try to do it in 3 dimensions, what you will do is basically revolve that around the z-axis. So what you see, it is a paraboloid. Okay, now then this is my x-axis, now this is my y-axis, like that. Okay, let me make this solid here. Now the second equation, z equals to r, pretty much done the same way. If this is r and this is c, this is r, z equals to r, then again the r is only positive. Now then I will revolve, to get it in 3 dimensions, I will revolve this with respect to the z-axis. Okay, and then this is what it looks like in 3 dimensions. So the r now becomes y. Well, basically that's because r basically the distance from the origin on xy plane. Now if I put these two graphs together, then let me put this into here. So basically you will put the cone into that paraboloid. This is the one back there here. Okay, and then this is what you get. Okay, so this is a solid which is bounded above by the cone and bounded below by the parabolic. Okay, and we can see that where do they intersect? Well, z equals to r squared and z also equals to r, so they intersect when r equals to 1 and r equals to 0. Okay, and you can tell why. Well, because they intersect at the origin, right? And then they also intersect at the height z equals to 1, the r equals to 1. Okay, now that's the sketch. Now let's put them into the situation here. So if I try to graph that nicely, let's say this is my x, this is my y, this is my z, and let me try to graph the cone first. I know this is not, this will not be as good as what we like to be. I try my best. Let's say this is the situation where the cone intersect with the paraboloid. inside cone. No, if I try to draw them all together at once like this, I believe you will get confused. But that's why I drew that thing earlier. Here, to accentuate that this is the intersection of the red cone and the black parabolic. Okay, now if you see it right now, you need to really pay attention to a lot of details to get what we are trying to graph. Okay, now but let's start now with the volume. You know that this graph is cylindrical, which means that it is symmetric with respect to z-axis. Okay, now if let's use triple integral. You can use double integral if you want, and you will see that later what happened. This will be from 0 to 2 pi for the theta, and the radius will be from 0 to 1, right, because they intersect at r equals to 0 and 1, right? So r squared equals to r. This is what I did earlier on the sketch paper. Okay, and then when you look at this solid is bounded below by the parabolic, which is z equals to r squared, and bounded above by z equals to r by the cone. Okay, and then inside you will see r dz dr d theta. Now if you try to use double integral to express the volume, let me call this volume E. If you try to find the volume using double integral, I believe this is what you will see. If you integrate this respect to z, you will have r squared r dr d theta. Right? I hope that you see that it is in line with what we learned before. If you use double integral, this is the domain of the integration. This is the upper function, and this is the lower function, right? And then, well, you see that there's no dz there. I mean, there's no z inside this integration, so it will be just r minus r squared. And notice also that not only the integrand is separable, it is independent of theta. In other words, I can pull the theta out, and that's basically the interval length for this, which is 2 pi, and I need to integrate the guys inside. There's r squared minus r cubed dr. This becomes 1/3 r cubed minus 1/4 r to the 4th from 0 to 1. Right? And then if I plug in 1, it becomes 1/3 minus 1/4. If I plug in 0, that's 0. Now of course at this level I assume you can compute that yourself quite fast, right? Then we see that the volume is pi over 6. Okay, now that's for number 1. 1a. 1b, the surface area of E will be equals to, let me use different color here. This is the surface area, the surface area of the paraboloid plus the surface area of the cone. Okay, now let's first deal with the surface area of the paraboloid. Okay, now you see that, let me do the setup first below. you see that z equals to r squared, which is z equals to x squared plus y squared, which means z sub x equals to 2x, z sub y equals to 2y, and then c sub x squared plus c sub y squared plus 1 equals to 4x squared plus 4y squared plus 1. Okay, now so the surface area of the parabolic will be given by double integral of the domain of the integration. You will see that d actually later on is the unit circle, and here the integrand will be 4x squared plus 4y squared plus 1 dA. Now I use d and dA for now because we know you will make it into polar integration, right, which is equals to then this is from 0 to 2 pi, and this is from 0 to 1, okay, and square root of 4r squared plus 1 r dr d theta. Now again, as earlier, it is independent of theta, so I can pull that out, right? And then let me use substitution here. U equals to 4r squared plus 1 such that du equals to 8r dr, which means my integral right now, oops, I don't have enough space here, will be, let me do it here, will be from 0 to, not 0 anymore, so 1 to 5 u to the power of 1/2 and du over 8, okay, which is equals to pi over 4 times 2 over 3 u to the power of 3/2 from 1 to 5, to cross cancelling thingy, pi over 3, and then 5 to the 3/2 minus 1, or maybe if I write it using radical, it would be pi 5 radical 5 minus 1 over 3. That's for the surface area of the parabolic. Now how about the surface area of the cone? Surface area of the cone, if you learned geometry before, and let's say this is our cone here, let's say this is R and this is the L, then the lateral area of that cone, in excluding the base, just the sides here, that's equals to pi RL, and in this case the cone has base radius 1, and the L, which is this length here, right, if you see the right part here, that's a square root of 2, right, okay, that's square root of 2, so that will be square root of 2 pi. Okay, now with that, then the surface area of the solid, let me write it down here, surface area of the solid equals to pi 5 radical 5 minus 1 over 3 plus radical 2 pi. Okay, that's the surface area of the solid. Now of course you are interested, you may be interested with this, Thomas, what happened if I want to do it using calculus? Okay, then we need to set it up better. C equals to R, or C squared equals to R squared. Yeah, you can do the square root thing, but I tend to keep myself as simple as possible. 2z sub x equals to, oh, I'm sorry, this is x squared plus y squared, right? Okay, so this is 2x, therefore c sub x equals to x over z, which is x over square root of x squared plus y squared. Symmetrically, the z sub y will be y over square root of x squared plus y squared. Now therefore c sub x squared plus c sub y squared plus 1 equals to x squared over x squared plus y plus y squared over x squared plus y squared plus 1, right? But these together equals to 1, so that thing is equals to 2. Now then, the surface area of the cone, if we use calculus 3 to do it, maybe another way to say it, if you use a hard way to do it, it will be, let me pull it up, I'm sorry, this is from 0 to 2 pi, right, and 0 to 1 square root of 2 r dr d theta. Let me pull the square root of 2 out, and I hope you realize that this integral here, this multiple integral here, this is the area of the domain, right, which is a circle with radius 1. Of course, you can do it regularly. If you want, you can do it regularly again, but use your intuition when you do some integral, right? And this will be pi r squared, which is again radical 2 pi. That's what we expect to get earlier, right, using the result we have from geometry. Therefore, this will be our result in the total surface area for solid E. Okay, this is for summer 2011, Math 263, Test 3, number 1, A and B.